everybody. We are Table 7. The voices you're hearing today are me, Allison Zillick, Ryan Cedel, and Owen Weber, but we also worked with Logan Ngyuen, Jonathan Marrero, Michael Thorwart, and Jace Collins. So we were tasked with creating a system that captures unused or wasted energy. The system had to serve a purpose and be creative, and it also had to be durable and sustainable enough to last a week unattended in our building PFT. So the specific customer objectives that they gave us were mechanical energy from available or otherwise unused or wasted resources, a useful form of energy, creative form of energy, and a sustainable form of energy. So filtering those into a house of qualities, we decided that we would break the house of qualities down into functions, ease, safety, and design. And from there, we identified where PFT occupants, manufacturers, marketers, and buyers would rank these qualities. The PFT occupants prioritized usefulness and convenience, the manufacturers prioritized cost and functionality, and the marketers prioritized aesthetics and safety. Now, arguably one of the most important the customer prioritized cost, benefits to the user, and maintenance. So the three design ideas that we created were the handrail, the door hinge, and the trash lid. The first design idea, the handrail, pulled a string upstairs and then rotated gears and motors with that motion, and then also rotated them again when you dropped it and used potential energy to bring the weighted handle back down. However, this would be difficult to build, it wasn't very self-explanatory, and it required a lot of extra external involvement from students, so we decided that this wasn't the best unintended idea. The second idea that we had was the door hinge. It had more energy potential, however, because it was on the top of a door, it was a harder installation process. It was a little harder to build, and also we felt like it was a less creative idea, ultimately choosing not to go with it. The third design idea that we had was the trash can lid. It had a similar design to the door hinge, where it used the rotation of an opening of a mechanical device to rotate gears, which then rotated a motor. However, it used an already pre-existing trash can all around PFT, and it fit seamlessly into everyday activities. It did not require maintenance. It required minimal external use from students, and we thought it was the much more creative idea out of the bunch. To condense our ideas and thoughts about why the trash can lid, idea number 3, was the better design idea, we created a decision matrix to finalize our idea. We compared the stair holder, the trash lid, and the door hinge, using the door hinge as our datum, and looking at the way that it captures energy, the creativity, the ease, the safety, and the design. The trash can lid, by far, is a better decision idea.
Okay, so these are our idea iterations of the trash can lid. Our first idea was to use a push lid with a single gear. You would push open the lid and it would turn the gear, generating electricity through a motor. We decided that this wouldn't work because the gear ratio is too low, so the motor wouldn't spin fast enough to generate enough electricity. Our second idea would be using a spool with a drawstring. Whenever you open it, it would pull the spool and do the opposite whenever you close it. But this would be obtrusive to the user. It would mess with throwing away trash. It would get in the way, and it would require additional springs and mechanical aspects to build. Also, in general, the push lid trash can would be hard to build around because there's a lot to work around. It's a small area. Okay, so this is the lid fusion model we went with. It's a top opening lid. The gear would be attached to the axis of rotation. It would spin gears to generate electricity through a motor, and this is the most seamless design that would fit into everyday activities because you have no outside input besides just throwing away your trash. The user doesn't have to actually put anything else into it. This is the modeling of the gearbox that we went with. This is like a mock iteration of what we thought we were going to do for the gearbox. We would attach the first gear to the axis of rotation, and it would turn gears through a system of ratios to make it faster and spin the motor to generate electricity, which would go to whatever we were going to power. From that fusion model, we generated our gearbox iterations. Our first design was a 4:5:1 gear ratio, and this gear ratio was too high. There was too many gears for the plastic. The axle was bending before there was any rotation. Design 2 was a 2:25:1 ratio. The gear ratio still wasn't ideal yet, and the primary axle was going to bend because there was too many gears. And the third design was the 1:25:1 ratio. There was minimal bending, but still a large enough gear ratio to spin the gears fast enough to generate electricity in the motor. And this theoretically would generate 1250 RPMs at 60 degrees per second.
Moving on to the actual building process, we began with lid construction. We used a drill press and various saws to prepare our aluminum L brackets and our plywood so that we could assemble them into the actual lid structure. After we finished the lid construction, we moved on to soldering the motor connections to the LED lights, and we used electrical tape to make sure that this connection was well insulated. Finally, we connected the gearbox to the lid, and this was probably the most difficult part of the entire build. In the end, we ended up drilling some holes into the side of the plywood on the top flap of the lid, where we drove some Lego axles into the side of the plywood and used those to hold a lever arm in place with the center of rotation of the axle on the lever arm aligned with the center of rotation of the hinges on the lid. And then we used plentiful amounts of hot glue and a bolt to attach the base of the gearbox to the base of the lid.
So this is our final design that we went with. It captures all of our objectives, that it harvests energy from the trash can lid. It uses the energy to power some LED lights that are going to be connected to a Christmas tree. And it can survive in the PFT for a week because it's out of the way. It incorporates everyday activities. You just open the trash can lid, throw away your trash, and close it. Our frame is very durable. It includes thick and durable wooden panels that are connected to hinges that hold it together, and metal brackets hold the lid to the trash can. This ensures that through the use of opening and closing it to throw away trash, it won't get destroyed. Also, for our gearbox, we included Lego pieces that have durable plastic and very high precision manufacturing from Lego. All the gears are kept firmly in place, and it's in a modular frame, and it's hot glued and bolted to our lid. This is our bill of materials. Our cost did come to $90, but most of our Lego pieces weren't used, and these Lego pieces could be used in the manufacturing process of more of these. Our most expensive thing was definitely that, and then we used some plywood, which we did get for free. So overall, our cost is not as high as it seems.
Moving on to some calculations related to the energy that we would harvest from this. Theoretically, the power generated by the lid opening is equal to the angular velocity times the force times the radius. So the radius from our model is 18 inches from the axle of the hinge to the handle. And estimating a total angular displacement of opening the lid to about 60 degrees and taking about half a second to 1 second to open the lid, we get an approximate angular velocity of 1 to 2 radians per second. F is just the additional force required to spin the gearbox. So estimating that we would need about 0.9 to 3.8 watts of power to power our LEDs. We can solve for force, and we get about 2 to 4 newtons of extra effort to open this lid, which we determined was negligible and probably not even noticeable for a user. The actual energy we got in testing, we obtained by using a 125 to 1 gear ratio. Using a multimeter, we measured about 0.06 amps and 2.4 volts, which gives a power output of 0.144 watts. Obviously, this is much less than our expected output, and we determined that this is due to physical constraints that limited the power output of the gearbox. Because of frictional forces and flexing in the axles in our gearbox, they actually could not handle the torque from the 2 to 4 newtons that we calculated. So these losses contributed to the difference between our theoretical power and our actual power. Finally, we determined some ways that our design can be improved. The primary problem we were having was that the plastic axle kept bending and was limiting our gear ratio to 125 to 1, and that the lights would only blink dimly for a fraction of a second before the lid stopped moving and the motor was no longer spinning. So to fix this, we could use a metal axle manufactured by Metal Technic Parts, which is a company based in Britain. The only reason we weren't able to use this in our current design is that The shipping took too long, and we wouldn't have been able to finish the project in our time frame. So with this steel axle, it would flex much less than the plastic axle, and it would allow us to use a higher gear ratio and to get a full rotation out of the gearbox without losing any of that movement to flexing. Another possible improvement is to use a flywheel on the motor axis to store excess power from a higher gear ratio. This would require more force to spin the motor, but because the force required to open the lid as it is already negligible, we decided that this would not create too much force for the user to still open the lid. With use of a one-way clutch, the flywheel could continue to spin even after the lid had stopped moving, allowing the lights to stay lit brighter even after the user stopped moving the lid.
And so last but not least, we had the objective of the system and method of energy capture is useful. So our listed goal, make PFT happy. What does this mean, and is our apparatus useful? So mental health during exam season, as I'm sure everybody knows, is at an all-time low. There statistically is a 39% decrease in students' mental health during exam season. Things such as perfectionism, feel of failure, lack of esteem, anxiety, depression, all of those weigh into that statistic. So how does our device help and promote usefulness? Well, we have Christmas lights and we have positive reinforcement. So how does this help? How is our apparatus useful? We have lights and we have positive reinforcement tied into our device. The lights promote dopamine, distraction, and a new perception during the exam season. When students see things such as Christmas lights, it creates a more positive outlook and it creates a little distraction from internal stressors and things like that. The positive reinforcement portion fosters a sense of achievement and momentary satisfaction. So when a student lifts up the lid and activates the lights to throw their trash away, there is a positive encouragement to repeat that behavior, which is beneficial towards long-term environmental care and improved student behavior. Additionally, to support these statistics and this research, how do LSU students specifically feel about this? We stood outside of our classroom and gathered the results of a study involving 6 males and 6 females that concluded that colored light can positively affect someone's mood. So what happened was that we had our apparatus and people threw their trash away, it lit up, and we evaluated with a survey how this influenced their emotions during exam season. The first survey evaluated how has your mental health been in the weeks before finals. The second survey, with the same 16 responses, evaluated how has interacting with the project affected your mood and quality of your day. According to these studies with 16 individuals, they concluded that colored lights had a positive impact on people's mood, and 81.4% answered that their mental health was either normal or struggling, but after interacting with the trash can, 87.6% of the people felt better. This supports that our device is useful in interacting with students during exam season, lifting their moods and alleviating stressors and pressure. And last but not least, our device had to be creative. The festive addition to PFT during Christmas time and during exam season was a very creative way to foster unused mechanical energy. And here is the live demonstration video of our apparatus. As you can see, the apparatus, you lift the trash can lid, and then as you lift it, the gears rotate, activating the motor, which then lights up our Christmas lights on the tree in the upwards motion and the downwards motion of the lid.
Yeah, we're gonna do a couple. Okay, go.
Here are our citations. Thank you so much for your time.